Hey everyone, and welcome. Let's dive right into this explainer and completely demystify the basic math that powers data structures and algorithms. A lot of times when we're writing code, we just kind of assume we need these massive, complex data structures to solve hard problems. But today, we're going to see exactly how a few surprisingly simple, fundamental math tricks can literally serve as a master key to crack open some seriously complex programming challenges. Now think about this for just a second. How do you actually teach a computer to read a number backward? It sounds ridiculously easy to us humans, right? We just look at it from right to left. But setting up the actual math to make a machine do this systematically and do it efficiently is a foundational building block in algorithms. So here is our roadmap for today's explainer. We'll be hitting 4 quick topics. First, the magic of modulo. Second, unlocking digit problems. Third, the square root shortcut. And finally, we'll wrap up with the Euclidean algorithm. All right, let's jump straight into part 1, the magic of modulo. Think of a really large number, kind of like an onion. To understand it or to manipulate it, we need a way to peel it apart layer by layer or, digit by digit. And we do this using a super simple logical loop. Step 1, we use an operation called modulo 10. Modulo just means we divide the number by 10 and grab only the remainder. And because our entire number system is base 10, running a modulo 10 always magically hands you the very last digit on the right. Step 2, we then just divide the original number by 10. Since we're storing this as an integer, it chops off the decimal, which literally removes that last digit we just pulled out. Step 3, we repeat. We just loop this modulo and division process over and over until our original number hits 0. It effectively peels the whole number apart from right to left. Moving right along to part 2. Unlocking digit problems.
So what's really cool is that we can take that modulo loop we just talked about and apply it directly to actual real-world technical interview questions. Check out these 4 common problems: counting digits, reversing a number, checking for a palindrome, and verifying an Armstrong number. Mastering that single, simple modulo extraction loop instantly gives you the power to solve every single one of these. Want to count digits? Just throw a counter variable into your loop. Want to reverse a number? Keep a running total, multiply it by 10, and add the extracted digit on each pass. Palindrome? Just generate that reverse number and check if it matches the original. It's the exact same underlying structure powering all these different solutions.
But let's zoom in on that 4th problem for a second. An Armstrong number is defined as a number that equals the sum of the cubes of its individual digits. Now, to solve this algorithmically, we absolutely don't need to invent some massive new framework. We just grab our trusty digit extraction loop, and instead of just counting the digits we pull out, we simply cube each one and add them all together. To put that into perspective, let's contrast a true Armstrong number against a false one. Take 371. We extract the 3, the 7, and the 1. 3 cubed is 27, plus 7 cubed, which is 343, plus 1 cubed, which is just 1. Add all those up, you get exactly 371. It matches perfectly. Now compare that to 35. 3 cubed is 27, plus 5 cubed, which is 125, and that gives us 152. Which obviously does not equal 35. Boom! Our basic math loop proves it instantly. Now, the crucial point here isn't just that this works, it's how unbelievably fast it works. The time complexity for this extraction loop is big O of log base 10 of n. Why? Well, because we are literally chopping the number by 10 on every single iteration. Whenever an algorithm's runtime is based on aggressively dividing the input size like that, you achieve incredibly fast logarithmic time. It is a total game changer. Okay, let's keep the momentum going with part 3, the square root shortcut. Here is where we meet the main antagonist in all of programming: time complexity. When you're dealing with massive, massive numbers, checking variables in linear time, meaning you step through every single number one by one, it just won't cut it. It eats up way too much computing time. We need a shortcut. So let's say we need to find all the divisors of the number 36. If you map out the factor pairs, you start to notice this really cool symmetry. Look at this. 1 times 36, 2 times 18, 3 times 12, 4 times 9, and then we hit 6 times 6. If we were to keep looping linearly past 6 to find the next factor, the very next pair we'd hit is 9 times 4, then 12 times 3. Do you see it? It's just mirroring the exact same pairs we already found right after we hit the number 6. Actually, there's a great quote from our source material that hits the nail on the head here. Beyond the square root, the numbers will grow and it will be nothing but a replication of the upper half. The square root of 36 is 6. So once we loop up to 6, we've essentially found both halves of every single factor pair. We literally don't need to keep searching. So by artificially stopping our search loop exactly at the square root of a number, we take our painfully slow linear O of n time complexity and we just smash it down to a highly optimized big O of square root of n. Think about that for a second. Imagine checking a number like 1 million. Instead of looping 1,000,000 times to find its factors, you only have to loop 1,000 times. That is a massive, massive optimization. And the best part? We can use this exact same trick for prime numbers. A prime number is strictly defined as a number that has exactly 2 factors, 1 and itself. Because of that rule, we can run our square root shortcut to verify primes with maximum efficiency. Instead of checking every single number up to n, we only check up to the square root of n. If our optimized loop finishes and only finds 2 total factors, we know for absolutely sure we've got a prime number.
All right, bringing it home with part 4, the Euclidean algorithm.
Let's unlock the Greatest Common Divisor, or GCD, by forging our most advanced mathematical key yet. To really appreciate how good this is, let's remind ourselves of the pain of the brute force approach first. Imagine you need to find the GCD of 52 and 10. The brute force method means iterating linearly downwards, stepping down from the smaller of the 2 numbers. So you'd start at 10, then check 9, then 8, stepping down one by one until you finally hit a number that cleanly divides both 52 and 10. As you can guess, this costs way too much time.
So let's optimize this with the Euclidean algorithm. Now, the underlying math says the GCD of 2 numbers is the exact same as the GCD of their difference. But constantly subtracting 10 from 52 is just slow. And what is repeated subtraction, really? It's division. So we bring back our old friend modulo to aggressively truncate the numbers. Step 1, 52 modulo 10 gives us a remainder of 2. Step 2, we pair the smaller number, 10, with that new remainder, 2. Step 3, repeat the modulo, 10 modulo 2. Step 4, 10 divides by 2 perfectly, leaving a remainder of exactly 0. By jumping straight to the remainders, we just skipped dozens of totally unnecessary subtraction steps.
And here is the absolute golden rule of the Euclidean algorithm. When you loop this modulo truncation, the very second one of the numbers hits 0, the other number is your greatest common divisor. No exceptions. We finished our sequence with a 0 and a 2, therefore 2 is our GCD. It is literally that simple, and it's incredibly powerful. Because the modulo operation shrinks the numbers so wildly fast, actually following a mathematical pattern tied to the golden ratio, or phi, this algorithm results in a beautiful logarithmic time curve, big O of log base phi of the minimum of A and B. I know it's a bit of a mouthful, but it means it's blazingly fast, highly optimized, and frankly, it's exactly the kind of elegant logic that technical interviewers absolutely love to see. Wow, okay, we have covered a massive amount of ground today. You have definitely leveled up. You've seen how to peel apart digits with modulo, identify prime numbers in a flash by stopping at the square root, and aggressively hunt down common divisors using logarithmic math. So my final question to you is this. Now that you've mastered these foundational math keys, what complex algorithm are you going to conquer next? Maybe you'll take these skills and dive straight into basic recursion? Think about it, keep practicing, and keep building those coding muscles.